All right, today we're going to be talking about how to determine which function type we're looking at. We're going to have a total of 3 function families by the time we're done with algebra. We're going to have linear, quadratic, and exponential. You should be setting this up on the page that has determining function type, the QR code for determining function type in the bottom. Well, I think I actually have it in the bottom left corner, but you should have that on the bottom of the facing page. And then you want to title it determining function type, and you want to put 3 headers: linear, quadratic, and exponential. And you kind of want to give a little bit of extra space to the quadratic column because we got to do a little bit more on one of these for one of the things we're going to be looking at. Take a moment right now and get that set up. All right, I've zoomed in so that we can see a little bit better what I'm writing here. So again, we're starting up at the top with graphs. You can like write graphs over here if you want to, but I hope that you'll be able to tell that we're looking at graphs. So we're going to draw, again, we're sketching graphs. We're not like drawing perfect graphs. Okay, so we're going to sketch a little coordinate grid in each one of these spaces so that we can just sketch to remind ourselves what these graphs look like, or in the case of quadratics, to discover what they look like. All right, so our linear graphs. A linear graph is simply a straight line. So let's write that down. A straight line. Okay, so we had 4 different types of lines we saw with 4 different slopes. We had positive slope, we had negative slope, we had up and down or undefined slope, and then we had 0 slope. So this is 0, this is undefined, this one is positive, and this one is negative. Okay, now remember, technically a line with undefined slope is not a function, but again, it's part of the linear function family, so we're going to kind of group it in there with that, with the linear family. Okay, now let's jump over to exponential because that's the one that we have actually seen before. Okay, so an exponential function has something called an exponential curve. Exponential curve. Okay, and if you recall, we had increasing, and that exponential curve kind of looked like that if it was increasing, and if it was decreasing, it looked like that. And again, these are both examples of exponential curves. Okay, now when you get into, for algebra 1, we have increasing and decreasing, and they only look like this. You might see ones in algebra 2 that look like that, but that's not for us. That's for later. That's future you gets to deal with that. Okay, but for now, that's not for us. Okay, so the new thing that we're learning right here is our quadratic function, and what we call a quadratic function is we call it a parabola. Okay, and for us, what that looks like is it starts at a point and it increases in both directions. And I know it doesn't look like it because, you know, whatever, but they are symmetrical. So like when you draw these parabolas, imagine like a line going through them, and if you folded them over, they would be exactly the same on both sides. Okay, so they could open upwards or they could open downwards, but they're going to have that same shape. Now, when you get into algebra 2, you might see ones that open sideways, but that's not what we're looking at. That's not quadratic. That's y equals square root of x, or x equals y squared, and that's not what we're looking at right now. Okay, so we are looking only at quadratic functions that open up or down. Okay, so that's graphs. Okay, so I'm going to go ahead and write graphs over here. I would hope that you wouldn't need to, but if you want to, go right on ahead. Okay. Once you're done with that, draw a line. Again, remember we need to save room for 2 other categories. So let's go ahead and scooch on. Let me zoom out so you can kind of see how much room I use there. I'm going to use probably, well, you'll see. We want to save a fairly decent sized chunk for the bottom. Okay. So let's zoom back in and let's talk about equations. So, oopsie, I didn't mean to do that. Hold on, let's use green. Equations, okay? So for equations, an example of a quadratic equation might be y equals x plus 5, okay? Now I'm all about those invisibles, right? So if I added in my invisibles on this one, I would have an invisible 1 coefficient, invisible 1 coefficient and an invisible 1 exponent, okay? So when I look at a linear function, the highest exponent I'm going to see I'm going to have a highest exponent of 1 or invisible. So it'll either be 1 or invisible, not both, okay? So I'll see 1 or invisible, all right? Now, again, if we jump over here to the one that we know, which is exponential, I have y equals, let's say 2 times 3 to the x. Now for this one, we notice that x is our exponent. X is our exponent up there. Okay, so what we notice about exponential functions is the input variable, I'm just going to abbreviate that, x is the exponent. Okay, so whenever we see our exponent our exponent up there in the our variable in the x position, in the exponent position, that's when we know we've got an exponential function. Now, the next one that we've got is our new function, which is our quadratic function. Now, quadratic functions look a little different. Y equals, here's an example, y equals x squared minus 6x plus 5. Now again, if I go in and I add in all my invisibles, I see I have an invisible 1 coefficient there. I've got an invisible 1 exponent there, okay? But what is the highest exponent you see? It's not 1. This isn't linear because it's got something higher than 1. What I see as my highest exponent is 2, okay? So for a quadratic, my highest exponent, I have a highest exponent of 2. Okay? Now, there's one thing that holds true for every single one of these. Okay, so we're actually going to I'm going to actually highlight this because it's that important once I get done writing it down. Okay, it's not just, so I don't know if any of you noticed, but I said the highest exponent is 1. But what if you had a negative exponent? Okay, if you had a negative exponent, let's just see if you can remember, where would that negative exponent be? If I followed my exponent rules, what would I have to do to that negative exponent to make it positive? So let's say I had like x to the negative 1. Well, hopefully you guys remember that when we have a negative exponent, what happens is that exponent moves into the denominator. We are not allowed to have exponents in the denominator for these 3 functions. So I can't have like over x. I can't have variables in the denominator because that's a different kind of function. That's not our function. That's Algebra 2's function. Okay? So we're going to make a note here. And then we're going to highlight it because it's that important. Variables are not in denominator. And we'll do a little example here. We'll say like y equals 2 over x, or y equals, let's just not do the y equals because I don't have room for that, or 2x to the negative 1. Okay, so we're not going to have negative exponents. We're not going to have variables in the denominator. And again, this is so important, I'm going to highlight it. Okay. All right. So again, a recap. When we have a linear function, our highest exponent is going to be 1 or invisible. When we have a quadratic function, our highest exponent is going to be 2. And if we have an exponential function, our variable is going to be there. Our exponent is going to be a variable. And we are never going to have a variable in the denominator for any of these function families. Now, this does not mean we will never, just not for these function families. Okay? Let's draw another separator line, and we will talk about the last way that we look at these three functions, which is in a table. All right, I think I saved enough room. Go me. So this is in a table. All right. So when I look at a table, let's start by making up a little linear table. Hang on a second. Let me pause. I'm going to actually grab a little bit slightly darker pen so we can see this a little better. There we go. Okay, so for this one, actually it's going to have 4 rows. We're going to do -1, 0, 1, 2. Now, again, we've seen a bajillion tables. We know they don't always go 1, 2, 3, 4, one right after the other with only spaced one apart. But for this example, so that I can explain to you how it works, we will. Okay, so the first ordered pair is going to be -1, 7, and then 0, 4, 1, 1, 2, -2. Now, you should all be real familiar with linear by now. You should know that when we're looking at a linear function, we are going to be finding delta y over delta x. Okay, now as I said, for the examples we're doing today, our delta x is always going to be 1, but let's go ahead and take a look at it. Okay, so I have 7 minus 3 is 4, 1 minus 1 is 0, I'm sorry, plus 1 is 0, 4 minus 3 is 1, 1 plus 1, 1 minus 3, 1 plus 1. Now, when I look at my delta y over delta x, it's the same for every single row. Okay, it's -3 over 1. Here, let me zoom in a little bit so we can see that a little better. It's -3 over 1, -3 over 1, -3 over 1. It's always the same. Okay, so what does that tell us? That tells us that delta y over delta x is constant. Okay, it's constant. We are going to need this little space down here, so don't go crazy. All right. Okay. Now, again, we're going to scooch on over here to exponentials because they are what we. Well, actually, let's do quadratics, okay? So this time, let's make our table, but let's make it kind of scooch it a little bit over, like so that we have some extra space over here, which I did not do. So let me try again and do better this time. Okay, whatever. All right, so for this one, I'm going to give you 4, 5, 6, and 7 for our x's. Our y's is going to be 4, -3. 5, 0, 6, 5, and 7, 12. Okay? So, again, let's try the same thing. Now, we know, you know because I told you that this is not quadratic. Okay? I mean, sorry, that this is not linear. But let's try our delta y over delta x and just find out. So, -3 plus 3 is 0. 4 plus 1 is 5. So far, so good. 0 plus 5 is 5. 5 plus 1 is 6. So I already see I don't have that constant delta y over delta x that I want to see. 5 plus 7 is 12. 6 plus 1 is 7. So delta y over delta x isn't constant. Let's prove it. Delta y over delta x. So I have 3 over 1, which is 3. Well, I'm not even going to bother. Yeah, which is 3. Let me scoot this over a little bit. Sorry, you guys. So my delta y over delta x for the first row is 3 over 1, which is 3, and then 5 and 7. Well, that's not right. That's not it. So now so for quadratic functions, in order for us to find that common rate, that constant rate, I got to go again. So I can't use delta y over delta x. I can't go out once. I have to go out twice. So I'm going to make another column here called delta y2. So instead of going once, I'm going to go twice. 3 plus 2 is 5. 5 plus 2 is 7. Now I have a common delta y2 over x. Okay, so for quadratics, delta y2 over delta x is constant. We call delta y2 the second difference. So what do you think we call delta y over delta x? Okay, well, technically, it's delta y1 over delta x, so we call this the first difference. We call using tables to figure out what function we're looking at, we call that finite differences, because what that means is, so infinite means it goes on forever. Finite means I only have to go so far in order to find a common difference. So for example, if I had to go out 3 times, then my exponent would be the third power. But since I have to go out twice, that means my exponent is going to be to the second power, and that makes it quadratic. If I have to go out 3 times, it would be to the third power, which makes it cubic, which again is an algebra 2 problem. If I had to go out 4 times, that would make it a, I don't know what the fourth one is, I'm not going to lie to you, but to the fourth power, okay? So that's quadratic. Let's take a look at exponential. Now, exponential, as we know, is completely different, okay? So let me give you an exponential function here. Okay, for our exponential function, x, y, let's do 0, 1, 2, 3, and we'll do 2, 6, 18, 42. Now, if I added 2 plus 4 is 6, 6 plus 4 is not 18, okay? And the next thing that we learned to do was to multiply. So instead of adding, I would say 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 42. So for an exponential function, there is no difference. We have a common multiplier, which we call our growth factor. Okay, so let's